Visit parthikachana.com for technology resources and stock analysis. 50 advanced level Hadoop interview questions with answers. 1. Explain the concept of data lineage in Hadoop. Answer. Data lineage is the ability to track the history and transformation of data from its source to its destination. It is crucial for understanding data quality, ensuring data integrity, and complying with regulations. 2. Describe the role of a data lake in modern data architectures. Answer. A data lake serves as a centralized repository for storing raw data in its native format. It provides flexibility for various analytical use cases, supports data discovery, and enables organizations to leverage the full potential of their data assets. 3. How can you optimize data ingestion performance in Hadoop for large datasets? Answer. To optimize data ingestion performance, consider the following strategies. Parallel ingestion. Use tools like Flume or Scoop to ingest data in parallel. Compression. Compress data before ingestion to reduce storage and network overhead. Partitioning. Partition data to improve query performance. Data locality. Ensure data is stored on the same nodes as the tasks that need to access it. 4. Explain the concept of rack awareness in HDFS. Answer. Rack awareness is a feature in HDFS that helps to improve data locality by placing replicas of a block on different racks within a data center. This reduces the likelihood of data loss due to a single rack failure. 5. How does Hadoop handle data replication and fault tolerance? Answer. Hadoop replicates data blocks across multiple data nodes to ensure redundancy and fault tolerance. The replication factor can be configured to determine the number of copies of each block. If a data node fails, the name node can replicate the lost data from other data nodes. 6. Describe the role of the name node in HDFS. Answer. The name node is the master node in HDFS responsible for managing the file system. It keeps track of the location of data blocks, handles client requests, and ensures data consistency. 7. Explain the concept of combiners in MapReduce. Answer. Combiners are functions that can be applied to intermediate key-value pairs before they are sent to the reducers. They can reduce the amount of data transferred between the map and reduce phases, improving performance. 8. How does WiseRN handle resource allocation and scheduling? Answer. Yarn uses a fair share scheduler by default, which ensures that resources are allocated fairly among different applications. Other schedulers like the capacity scheduler and the first-in, first-out scheduler can also be used based on specific requirements. 9. Describe the role of the application master in YARN. Answer. The application master is a process that represents an application in YARN. It negotiates resources from the resource manager, coordinates the execution of tasks, and monitors the application's progress. 10. Explain the difference between partitioning and bucketing in Hive. Answer. Partitioning divides data into smaller partitions based on a specific column, which can improve query performance for filtering on that column. Bucketing distributes data evenly across buckets based on a hash function, which can improve query performance for aggregations and joins. 11. How does HBase handle data consistency and availability? Answer. HBase uses a write-ahead log, WEL, to ensure data consistency. It also replicates data across multiple regions to improve availability. 12. What are some best practices for optimizing Hive queries? Answer. Partition and bucket data appropriately. This can improve query performance for filtering and aggregation operations. Use appropriate data types. Choosing the correct data types can reduce storage overhead and improve query performance. Avoid unnecessary joins and aggregations. Simplify queries to reduce the amount of data processed. Use indexes. Create indexes on frequently queried columns to improve query performance. 13. Explain the concept of RDDs in Spark. Answer. RDDs, resilient distributed datasets, are the basic data structure in Spark. They are immutable collections of objects that can be distributed across multiple nodes in a cluster. 14. How does Spark handle fault tolerance? Answer. Spark uses lineage to recover lost data in case of failures. It can recompute lost partitions by tracing the lineage graph. 15. What is the difference between Spark SQL and Spark Core? Answer. Spark SQL, a component of Spark that provides SQL-like capabilities for working with structured data. Spark Core, the core engine of Spark that provides the basic API for working with RDDs. 16. How can you ensure data privacy in a Hadoop environment? Answer. To ensure data privacy in a Hadoop environment, you can implement the following measures. Access control. Restrict access to sensitive data based on user roles and permissions. Encryption. Encrypt data at rest and in transit to protect it from unauthorized access. Data masking. Replace sensitive data with random or synthetic values for testing and analysis. Regular audits. Conduct regular audits to identify and address security vulnerabilities. 17. What are the challenges of working with large datasets in Hadoop? Answer. Working with large datasets in Hadoop can present several challenges, including data ingestion, efficiently ingesting and processing large volumes of data. Data quality, ensuring data accuracy and consistency. Performance optimization, optimizing job execution to handle large datasets efficiently. Storage management, managing storage costs and capacity planning. 18. How can you optimize the performance of Hive queries? Answer. To optimize the performance of Hive queries, you can partition and bucket data appropriately. This can improve query performance for filtering and aggregation operations. Use appropriate data types. Choosing the correct data types can reduce storage overhead and improve query performance. Avoid unnecessary joins and aggregations. Simplify queries to reduce the amount of data processed. Use indexes. Create indexes on frequently queried columns to improve query performance. 19. Describe a real-world use case of Hadoop in the healthcare industry. Answer. Hadoop can be used in healthcare to analyze medical records, identify disease patterns, and improve patient outcomes. For example, it can be used to analyze genomic data to develop personalized treatment plans. 20. How is Hadoop used in the field of big data analytics? Answer. Hadoop is widely used in big data analytics for tasks such as web log analysis, understanding user behavior and website traffic patterns, social media analysis, analyzing trends and sentiment in social media data, financial data analysis, detecting fraud and identifying market trends, scientific research, processing large datasets from scientific experiments. 21. Explain the concept of Delta Lakes. Answer. Delta Lakes are a platform for building data lakes that are reliable, scalable, and ACID compliant. They provide features such as version control, time travel, and batch and streaming capabilities. 22. What is Apache Tez, and how does it improve performance in Hadoop? Answer. Apache Tez is a data flow engine that can be used to execute various data processing tasks, including MapReduce, Pig, and Hive jobs. It provides a more flexible and efficient execution framework compared to Yarn's default scheduling mechanisms. 23. How can you optimize the performance of Spark applications? Answer. To optimize the performance of Spark applications, you can choose appropriate data structures. Select data structures that are well-suited for your specific use case. Use caching effectively. Cache frequently accessed data to improve performance. Broadcast large datasets. Broadcast large datasets to all executors to avoid unnecessary network transfers. Optimize data partitioning. Partition data appropriately to improve data locality and reduce shuffle overhead. 24. What is the role of the name node in HDFS? Answer. The name node is the master node in HDFS responsible for managing the file system. It keeps track of the location of data blocks, handles client requests, and ensures data consistency. 25. What is the difference between a block and a chunk in HDFS? Answer. Block. The basic unit of data storage in HDFS. The size of a block is configurable. Chunk. A smaller unit of data that is used for network transmission. 26. What is the purpose of the data node in HDFS? Answer. The data node is a slave node in HDFS responsible for storing data blocks. It handles requests from the name node to read and write data blocks. 27. What is the role of the job tracker in Hadoop 1? Answer. The job tracker is the master node in Hadoop, one responsible for scheduling and monitoring MapReduce jobs. It assigns tasks to task trackers and tracks the progress of jobs. 28. What is the purpose of the task tracker in Hadoop 1? Answer. The task tracker is a slave node in Hadoop 1 responsible for executing MapReduce tasks. It receives tasks from the job tracker and reports the status of the tasks to the job tracker. 29. What is the difference between a primary name node and a secondary name node in HDFS? Answer. Primary name node. The main name node responsible for managing the HDFS file system. Secondary name node. A backup of the primary name node that periodically merges edits logs and creates checkpoints to ensure data consistency. 30. What is the purpose of the name node edit log? Answer. The name node edit log is a journal of changes made to the HDFS file system. It records operations such as creating, deleting, and modifying files and directories. 31. What is the purpose of the name node checkpoint? Answer. The name node checkpoint is a snapshot of the HDFS file system state. It is used to recover the file system in case of a name node failure. 32. What is the role of the resource manager in YARN? Answer. The resource manager is the master node in YARN responsible for allocating resources to applications. It coordinates the node managers and manages the application lifecycle. 33. What is the role of the node manager in YARN? Answer. The node manager is a slave node in YARN responsible for managing resources on a node. It reports resource availability to the resource manager and executes containers that are assigned to it. 34. What is a container in YARN? Answer. A container is a unit of resource allocation in YARN. It represents a specific amount of CPU, memory, and other resources that can be assigned to an application. 35. What is the difference between a resource queue and a capacity scheduler in YARN? Answer. Resource queue, a logical grouping of applications that share a common set of resources. Capacity scheduler, a scheduler in YARN that allocates resources based on the capacity assigned to each resource queue. 36. What is the role of the application master in YARN? Answer. The application master is a process that represents an application in YARN. It negotiates resources from the resource manager, coordinates the execution of tasks, and monitors the application's progress. 37. What is the difference between a Spark driver and a Spark executor? Answer. Spark driver. The master node in a Spark cluster that coordinates the execution of Spark jobs. Spark executor. A slave node in a Spark cluster that executes Spark tasks. 38. What is the purpose of the Spark RDD? Answer. The Resilient Distributed Dataset, RDD, is the basic data structure in Spark. It is an immutable collection of objects that can be distributed across multiple nodes in a cluster. 39. What is the purpose of Spark streaming? Answer. Spark streaming is a component of Spark that allows you to process streams of data in real time. It can be used for applications such as social media analytics, financial data analysis, and IoT data processing. 40. What is the difference between a map task and a reduce task in MapReduce? Answer. Map task processes a chunk of input data and generates key-value pairs. Reduce task combines key-value pairs produced by the map tasks and produces the final output. 41. How does Hadoop handle the small files problem, and what are some solutions to mitigate this issue? Answer. Hadoop Distributed File System, HDFS, is designed to store and process large files efficiently, but it struggles with handling a large number of small files. This is known as the small files problem. Each file in HDFS, regardless of its size, requires metadata storage in the name node. When there are too many small files, the name node becomes overwhelmed as its memory is limited. This leads to performance degradation, slower processing, and inefficient resource utilization since each file is treated as a separate block, even if it's smaller than the block size, usually 128 megabytes or 64 megabytes. To mitigate this issue, several strategies can be employed. 1. Use of HAR. Hadoop archives bundle multiple small files into a single file, reducing the number of file entries in the name node. However, Reading from a HAR file can be slower compared to reading from native HDFS. 2. Combined file input format. This is a MapReduce input format that can combine multiple small files into larger chunks, reducing the number of mappers needed for processing. This improves efficiency in job execution. 3. Sequence files or AVRO. Converting small files into sequence files or AVRO formats is a common practice. These formats store data as key-value pairs or binary formats, allowing multiple records to be packed into larger files, thus reducing the burden on the name node. 4. Use of HBase. For scenarios where small files need to be stored and retrieved efficiently, HBase, which runs on top of HDFS, can be used. HBase is a distributed, column-oriented NoSQL database that handles small data efficiently and can eliminate the small files problem. By applying one or more of these strategies, the small files problem in Hadoop can be managed effectively, improving performance and ensuring efficient use of name node memory. 42. Explain the concept of HDFS federation and how it differs from Hadoop high availability, HA. Answer. HDFS federation and Hadoop high availability, HA, are both mechanisms that aim to improve the scalability and reliability of Hadoop, but they serve different purposes and operate in distinct ways. HDFS federation. HDFS federation is designed to address the scalability limitations of a single name node. In traditional HDFS architecture, a single name node manages the entire namespace. As the size of the cluster grows, the name node can become a bottleneck due to the limitations of its memory and processing power. HDFS federation allows for multiple name nodes, each managing a portion of the HDFS namespace, called a namespace volume. Each name node operates independently, with separate block pools, enabling horizontal scaling of the name node layer. In this setup, each name node is responsible for a specific namespace, allowing for improved scalability and throughput. Block reports from data nodes are also divided among different name nodes, reducing the load on any individual name node. Applications can access multiple namespaces seamlessly, allowing for better isolation and multi-tenancy. Hadoop High Availability, HA. High availability in Hadoop ensures that the cluster remains operational even in the event of a name node failure. Traditionally, the name node was a single point of failure, SPLF, in Hadoop. HA addresses this by introducing a standby name node that takes over automatically if the active name node fails. Both active and standby name nodes share the same metadata and are kept in sync using a mechanism called the edit log journal. When a failover occurs, the standby name node is promoted to active, ensuring minimal disruption. The key difference between HDFS federation and HA is that federation is about scaling the name node for better performance, while HA is focused on improving reliability and fault tolerance. 43. What is speculative execution in Hadoop, and how does it improve performance in MapReduce jobs? Answer. Speculative execution is a feature in Hadoop MapReduce designed to improve the performance and reliability of job execution in a distributed environment. It comes into play when a MapReduce task is detected to be running slower than expected compared to other tasks. In a distributed cluster, various factors such as network latency, hardware differences, or uneven load can cause some tasks to execute more slowly than others. These slower tasks, often referred to as stragglers, can significantly delay the completion of the entire job. When speculative execution is enabled, Hadoop monitors the progress of tasks and identifies tasks that are significantly lagging behind. Instead of waiting for these slow tasks to complete, Hadoop launches duplicate, speculative, tasks on different nodes. The task that finishes first, whether it's the original or the speculative copy, gets accepted, and the results from the slower task are discarded. Speculative execution improves performance by reducing the impact of stragglers on overall job completion time, especially in heterogeneous environments. However, it also introduces some additional resource overhead since duplicate tasks are created. Therefore, speculative execution should be carefully tuned to avoid unnecessary resource consumption in cases where it might not be beneficial. 44. How does Hadoop handle schema evolution in data formats like Avro and Parquet, and why is it important? Answer. Hadoop, often used with semi-structured or structured data formats like Avro and Parquet, needs to handle schema evolution to support scenarios where data schemas change over time. Schema evolution refers to the ability to modify the schema, the structure of the data, without breaking existing applications or requiring a complete rewrite of the data. Avro. Apache Avro is a row-based storage format that stores both the data and its schema. Avro supports schema evolution by allowing new fields to be added to a schema or old fields to be removed, as long as certain rules are followed. When data is written, Avro stores the schema used to write the data alongside it, and when data is read, Avro can reconcile the schema used during writing with the schema expected during reading, the reader schema. This ensures compatibility between different versions of the schema. Avro supports backward compatibility. Newer versions of the schema can read older data. Forward compatibility. Older versions of the schema can read newer data, as long as new fields are optional or have default values. Parquet. Parquet is a columnar storage format designed for efficiency in analytical queries. Unlike Avro, Parquet does not store the schema alongside the data. However, schema evolution is supported by adding new columns or modifying existing ones, as long as certain compatibility rules are maintained. Tools like Hive and Impala, which work with Parquet files, can handle schema changes like adding new columns without requiring a full rewrite of the data. Handling schema evolution is crucial in big data systems like Hadoop because data schemas often evolve as business requirements change. Without schema evolution, changes to the data model would require costly rewrites of data or modifications to applications that consume the data, both of which can be resource-intensive. 45. Explain the role of Zookeeper in a Hadoop cluster and why it is critical for maintaining coordination. Answer. Zookeeper is a distributed coordination service that plays a critical role in managing and coordinating distributed applications like Hadoop. In a Hadoop cluster, Zookeeper is used for maintaining configuration information, providing distributed synchronization, and ensuring the coordination of services across the cluster. It is especially important in scenarios where high availability and fault tolerance are required. Zookeeper is essential in several components of Hadoop. Hadoop High Availability, HA. In an HA setup, Zookeeper is used to manage the failover process between the active and standby name nodes. It ensures that only one name node is active at a time, preventing split-brain scenarios where both name nodes think they are active. YJARN Resource Manager HA. Similar to HDFS HA, Zookeeper coordinates failover between active and standby resource managers in a YRN cluster. HBase. Zookeeper helps manage the coordination between HBase masters and region servers, ensuring efficient management of metadata and preventing conflicts. Locking and leader election. Zookeeper provides distributed locking mechanisms and leader election functionalities. In Hadoop, this is useful for scenarios where multiple nodes or processes need to coordinate access to shared resources. Zookeeper is critical in maintaining the consistency and reliability of a distributed system, ensuring smooth coordination among different components of the Hadoop ecosystem. 46. What are the limitations of the Hadoop MapReduce model, and how have modern frameworks addressed these limitations? Answer. The Hadoop MapReduce model, while revolutionary for processing large datasets in parallel, has several limitations that have been addressed by modern frameworks like Apache Spark and Apache Flink. Some key limitations of MapReduce include 1. High latency. MapReduce is disk I/O intensive, as intermediate data between the map and reduce phases is written to disk. This leads to higher latency, making it inefficient for low-latency applications or iterative algorithms like machine learning. 2. Rigid execution model. The MapReduce model follows a strict two-stage pipeline of map and reduce tasks, which makes it unsuitable for more complex data processing workflows that require multiple stages or intermediate computations. 3. Inefficient for iterative processes. MapReduce is not well suited for iterative processes like graph processing or machine learning, as it requires data to be read from and written to HDFS at every iteration. This results in a lot of overhead and poor performance for such tasks. 4. Resource utilization. In Hadoop, resource allocation is tied to the MapReduce execution model. This can lead to underutilization of cluster resources, as MapReduce jobs do not efficiently share resources between tasks. Modern frameworks like Apache Spark and Apache Flink address these limitations in several ways. In-memory processing, Spark, for instance, uses in-memory data processing through its resilient distributed dataset, RDD, abstraction. This reduces the need for disk I/O and improves performance for iterative algorithms. Directed Acyclic Graph, DAG, execution model. Spark uses a DAG-based execution engine, allowing for more flexible and efficient execution of workflows with multiple stages. Better resource management. Frameworks like Spark and Flink are more efficient at managing cluster resources, leading to better overall resource utilization compared to the rigid MapReduce model. Stream processing. Apache Flink, in particular, is designed for real-time stream processing, addressing a major shortcoming of the batch-oriented MapReduce model. Overall, while Hadoop MapReduce remains a foundational technology, modern data processing frameworks have evolved to provide faster, more flexible, and more efficient solutions for a wider range of use cases. 47. How does Hadoop handle data skew in MapReduce jobs, and what strategies can be employed to mitigate it? Answer. Data skew occurs in MapReduce jobs when the distribution of data across tasks is imbalanced, causing some tasks to process significantly more data than others. This can lead to inefficiencies, as the slower tasks, with more data to process, will delay the completion of the entire job. Data skew typically happens during the reduce phase, when some reducers get assigned a disproportionate amount of data due to uneven key distribution. To handle data skew in Hadoop, the following strategies can be employed. 1. Combiner. Using a combiner can reduce the amount of data that gets shuffled to the reducers by performing a local aggregation on the mapper side. This reduces the data volume and can help mitigate skew by reducing the workload on reducers. 2. Custom partitioners. The default Hadoop partitioner evenly distributes data based on hash values of the keys. However, in cases of skew, some keys may be much more frequent than others, leading to an uneven distribution of data across reducers. A custom partitioner can be used to distribute data more intelligently, ensuring a more balanced load across reducers. 3. Skew join optimization. In Hive and Hive, skew joins occur when one table has disproportionately large keys compared to others. Hive offers a feature called skew join optimization, which handles this by splitting the large key into multiple smaller chunks and distributing them across reducers. This helps balance the load and avoid bottlenecks. 4. Sampling data. Before running a full MapReduce job, it's often helpful to sample the data to understand its distribution. Based on this information, you can tune the partitioning or implement other optimization techniques to ensure an even distribution of data. 5. Increasing number of reducers. If data skew is unavoidable, increasing the number of reducers can help by spreading out the load across more tasks. However, this can lead to diminishing returns if the skew is extreme, so this approach is often used in conjunction with other strategies. 6. Salting keys. Salting is a technique where additional random values are added to the keys during the shuffle phase to ensure more even distribution. For example, instead of using a single key like user ID, you might create a key like user ID_salt. This creates more partitions and helps spread out the data among reducers. By employing these strategies, data skew can be mitigated, leading to more efficient MapReduce jobs and reduced processing times. 48. What is a side data distribution pattern in Hadoop, and how is it used in MapReduce jobs? Answer. Side data distribution is a pattern in Hadoop MapReduce used to distribute small datasets, also known as side data, across all nodes in a distributed system. This pattern is often required when a MapReduce job needs access to additional data that is relatively small compared to the primary dataset being processed. Common use cases include lookup tables, configuration files, or any supplementary data needed during processing. Since HDFS is designed for large-scale data, small datasets like lookup tables would not be efficient to store and access repeatedly from HDFS. Instead, side data distribution ensures that these smaller datasets are available to each node locally. There are two main approaches to achieve side data distribution in Hadoop. 1. Distributed cache. Hadoop's distributed cache mechanism allows small files to be cached and distributed to all nodes in the cluster. Once a file is added to the distributed cache, It is copied to the local file system of each node before the job begins execution. This allows mappers and reducers to access the side data as if it were a local file. For example, a lookup table that maps product IDs to product names can be distributed via the cache, allowing each task to refer to it during execution. Usage example:
Java.
Add a file to the distributed cache. Distributed cached, add cache file, new URI, /path/ to /lookup_table, job, get configuration. 2. Broadcast variables. In Spark, while this pattern is not native to MapReduce, in Apache Spark, a similar concept exists with broadcast variables. Broadcast variables are used to efficiently distribute read-only data to all worker nodes, where it is cached in memory. This minimizes the overhead of repeatedly shipping data across the network during each task execution. The side data distribution pattern is critical in situations where tasks running on distributed nodes need consistent access to the same small dataset without relying on the performance bottleneck of repeatedly reading from HDFS. 49. How does the shuffle phase work in a MapReduce job, and what optimizations can be applied to improve shuffle performance? Answer: the shuffle phase in Hadoop MapReduce is one of the most critical and resource-intensive stages of job execution. It occurs between the map and reduce phases, where the output of the map tasks, intermediate key-value pairs, is transferred, shuffled, across the network to the appropriate reduce tasks based on the key. The reduce tasks group the shuffled data by key before processing it. The shuffle process consists of two main parts. 1. Sort. The output of the map tasks is sorted by key. This sorting ensures that all values associated with a particular key are grouped together when they reach the reduce task. Sorting happens on each mapper and ensures efficient grouping for the reduce phase. 2. Transfer. After sorting, the intermediate data is transferred across the network to the reducers. This involves fetching the map outputs, key-value pairs, and transferring them to the reduce nodes. Given that the shuffle phase involves disk I/O, sorting, and network transfer, it can become a major bottleneck in large-scale jobs. To optimize the shuffle phase, the following techniques can be applied. 1. Compression. Compressing the map output before it is shuffled reduces the amount of data transferred across the network. Hadoop supports compression codecs such as gzip, Snappy, and LZO. Enabling compression reduces network bandwidth usage and speeds up the shuffle process. Example:
Java.
SONF-set. MapReduce, mapped output to compress, true. CONF-set. MapReduce, mapped output compress.codec, org, Apache, Hadoop.io.compress, Snappy codec. 2. Tuning buffer sizes. The size of the memory buffer used to hold the map output before writing to disk can be adjusted. If the buffer is too small, frequent spills to disk will occur, increasing I/O operations. By increasing the buffer size, fewer spills happen, improving performance. 3. Reduce number of spills. By increasing the size of the IO'd, sort, MB parameter, the buffer that holds map outputs, fewer spills to disk will occur. Reducing the number of spills decreases the amount of data that needs to be merged, leading to better performance. 4. Tuning number of reducers. The number of reducers should be appropriately set. Too few reducers can overload certain nodes with data, while too many can lead to overhead in task scheduling. By carefully setting the number of reducers, the shuffle process can be balanced across the cluster. 5. Combiner usage. Adding a combiner to perform partial aggregation on the mapper side can reduce the amount of data shuffled to the reducers. This is especially effective in cases where the reducer performs aggregations like summing or counting. 6. Network optimization. Since the shuffle phase heavily relies on network bandwidth, it is important to ensure that the network infrastructure is optimized. Using high-bandwidth networks, reducing network contention, and ensuring efficient routing between nodes can improve shuffle performance. By applying these optimizations, the performance of the shuffle phase in MapReduce jobs can be significantly improved, reducing overall job completion time. 50. Explain the concept of write skew in HBase and how it affects performance. Answer. Write skew in HBase refers to an uneven distribution of write requests across region servers, leading to performance bottlenecks. HBase stores data in regions, and each region is served by a region server. If write requests are not evenly distributed across the cluster, certain region servers may become overwhelmed with a higher volume of writes than others, leading to slower write performance and increased latency. Write skew can happen due to several reasons. Hotspotting. This occurs when a large number of write requests target a single region or a small subset of regions. Hotspotting is often caused by poor key design, where many write operations map to the same region. For example, if row keys are based on timestamps or sequential IDs, they may all end up in the same region. Inefficient region splits. If regions are not split correctly, or if the automatic region splitting mechanism is not functioning properly, some regions may end up holding much larger portions of data than others. This causes uneven write loads across the cluster. To mitigate write skew in HBase, the following strategies can be employed. 1. Pre-splitting regions. Instead of relying on automatic region splitting, which happens after a region becomes too large, pre-splitting regions based on expected data distribution can help avoid hotspotting. This ensures that data is evenly distributed across regions from the start. 2. Salting row keys. Adding a random salt or hash prefix to the row key can distribute write requests more evenly across regions. For example, instead of using a sequential ID as the row key, a salt can be prepended, ensuring that writes are spread across different regions. 3. Time-based partitioning. For time series data, where row keys are based on timestamps, it is important to partition the data by time windows, e.g., daily or monthly partitions, and assign each partition to different regions. This prevents all writes from being directed to a single region based on the current time. 4. Hotspot detection. Monitoring and identifying hotspots in real time using tools like Apache HBase's built-in metrics or external monitoring systems, e.g., Grafana, Prometheus, can help identify write skew issues early, allowing for corrective action before performance degrades significantly. By addressing write skew, HBase clusters can achieve more balanced write performance, improving both throughput and latency across the distributed system. Thank you for watching. Like, share, and subscribe. Visit parthakachana.com for technology resources and stock analysis.